Welcome to a lesson with Dr. Powell. Let's take a look at finding the interval of convergence of a power series. So a power series is like a function. You can input a value of x. So let's suppose we have something like this, x minus 2 raised to the n. So we're going to be cycling through lots of powers of n. So it's kind of like a polynomial, like an infinite polynomial. And we're going to have different coefficients. Let's suppose we have something like n squared all over something like n cubed plus 1 multiplied by 3 to the n. Okay, so what do we do? Well, the interval of convergence is the domain. It's like the values of x that we can plug into this as this function that would make it well defined. So that this sum actually works. What values of x can you actually plug in to make it work? Well, the way we do this, first of all, is we notice that the domain always works when x is 2. When x is 2, that works great because we get 2 minus 2, which is 0 to the n. So it's like we're adding up a lot of zeros, so we actually say the interval will be centered about 2. The interval of the domain will go this way and this way by the same amount. The amount that it goes in both ways is called the radius of convergence. Okay, so in order to do this, we're going to use the ratio test, which compares what we have here to a geometric type series. So the ratio test states that we can take the limit a sub n plus 1 times 1 over an, absolute value, as n goes up to infinity. And if this limit, we take this limit, and if this limit is less than 1, then we're guaranteed convergence. If it's actually greater than 1, we actually have divergence. And if it's equal to 1, we don't necessarily know. Equal to 1 will actually give us endpoints, but less than 1 will give us the radius. So let's get going. So how we first figure out a sub n plus 1 by replacing n everywhere. So think about this as being like a sub n. So what we do is we replace n everywhere with n plus 1 to get a sub n plus 1. So we would have n plus 1 squared x minus 2 to the n plus 1 all over n plus 1 quantity cubed plus 1, 3 to the n plus 1. So that's a sub n plus 1. Now we look at 1 over a sub n, which is like the reciprocal of what you see here. 3 to the n cubed plus 1 all over n squared x minus 2 to the n. And we are taking, okay, so we take a limit of this. And absolute values, well, this is completely positive the whole time. Okay, so notice we get cancellation here and here and here and here. And we're taking an absolute value. Notice that, okay, on the top, we have n plus 1 squared times n cubed plus 1. All that really is we're concerned about, we're taking a limit of like a polynomial over a polynomial, is the leading term. So leading term is going to end up being an n squared times an n cubed, so n to the 5th on the top plus some things, multiplied to the x minus 2 that's still there. On the bottom, we're left with a polynomial. It looks like n squared and a n to the n cubed. So it looks like n to the fifth. In fact, with that 3, it's going to be like 3 n to the fifth plus stuff. And we're taking a limit of this as n goes to infinity. And this part right here, just look at the leading terms to find the limit of this part. We'll get 1/3. 1/3 times x minus 2. So we're going to get absolute value of x minus 2 over 3. And that's less than, and we want this to be less than 1 for convergence. We multiply things by 3 here, we're going to get x minus 2 absolute value is less than 3. This absolute value means the distance x is from 2. And we want that to be less than 3. That means the radius is equal to 3. So we're going up to 5, and we're going down to -1. Now, we just need to test the endpoints to see if we include them or not. Well, let's plug in -1 and see what happens. When we plug in -1 into this series, we end up getting n squared -3 to the n all over n cubed plus 1 times 3 to the n. And we're taking the sum of that. So we're testing the endpoint right now. Okay. So now notice that, see this -3 to the n? We actually can rewrite that, distribute the power of n across the multiplication of -1 times 3 like this, which is nice because the 3 to the n's cancel. Now we're left with this series right here. Now, notice that it's alternating, and it's n squared over n cubed plus 1, which kind of, in some sense, looks a little bit like 1 over n, which we know diverges. However, since it's alternating, there's hope. All we need is that the terms are decreasing by the alternating series test. So let's see about that. How can we show that the absolute value of the terms are decreasing if we ignore the -1s? Well, we can take a derivative and see if the derivative is negative, and if the derivative is negative, then we know it's decreasing. So let's take a derivative by using the quotient rule. And we're just going to focus on this part right here, n squared over n cubed plus 1. So we take a derivative of the top, 2n, bottom, n cubed plus 1 using the quotient rule, minus the top times the derivative of the bottom, which is 3n squared, all over the bottom squared. Now, all we're interested in is if eventually the derivative will be negative. So we look at the leading term and check to see if it's negative. Leading term will be, we'll get a 2n to the fourth over here, and you'll get a minus 3n to the fourth over here. Notice you'll get a negative n to the fourth. That shows us that eventually the derivative is negative. Therefore, eventually it's decreasing. Since it's decreasing and alternating, it will converge, which means that -1 should be included. Now, let's take a look at 5. Should 5 be included? Well, all we need to do is plug it in and see what happens. So let's plug in x equals 5 into the series. Okay, we would end up getting 3 to the n squared n cubed plus 1 times 3 to the n. Those cancel. Then we're left with n squared over n cubed plus 1, which looks a lot like 1 over n. In fact, we can think that this is actually less than, eventually, for large enough n squared over n cubed. That's because we have the reverse inequality in the denominators, and clearly n cubed plus 1 is bigger than n cubed. So therefore we have this inequality this way, which is equal to 1 over n. Wow, well that means, well, for one thing, I guess that works a little bit, but not really. We want to show divergence. That we would use for convergence, but we know that 1 over n diverges. So we'd like to show that this is actually bigger. Well, we need a reverse inequality here. Let's see, n cubed plus 1 has to be less than n cubed in the denominator, which it's not. But it would be simple enough to just tack on a 2 here, and it would be okay. Because this is like n cubed plus n cubed, and definitely n cubed is bigger than 1 for big enough n. So that would work. So this is actually correct with 1 over 2n. But we know that that the series with 1 over 2n diverges by a p-test, because you can factor out the 1/2 and you have 1 over n. We know that 1 over n, the harmonic series, and goes from 1 to infinity, actually diverges. Hence, we'll actually get divergence. So we do not include 5 at that end. So the interval of convergence will be from -1 up until, but not including 5. So the interval is from -1, including it, and up until 5, but not including it. This is like the domain for this function, the x values that actually work to give a result. Thanks for watching.